Welcome to the ELECTRO-MASTER channel. In this video, I'll show you step by step how to repair an inverter manufactured by LS Electric, model M100, type LSLV0008M100, made in Korea. We'll analyze the problem, identify the faulty components, and replace them to restore the inverter to optimal functionality. If you're interested in electronics repair and want to learn more about this type of device, watch this video until the end. Let's get started. The first step is to perform a visual inspection of the inverter. This allows me to identify any obvious signs of damage, such as burnt components, loose wires, or other visible issues. Once I complete this check, I'll proceed to disassemble the device to access the interior and evaluate the situation in more detail. The first observed symptom is that the inverter does not display anything on the screen. This most likely points to an issue with the switching power supply. From my experience, this type of fault occurs when the power supply fails to generate the required voltages in the secondary circuit to power the rest of the device. This will be the main area to investigate to identify the root cause of the problem. The first step in troubleshooting is to measure the resistors that supply power to the MOSFET's power circuit. These resistors play a crucial role in the proper operation of the transistor, ensuring the control of current flow in the circuit. If one of them is burnt or has an incorrect value, it could lead to the failure of the switching power supply. I will use a multimeter to check their values and identify any potential issues. As can be seen, I discovered 4 resistors that are open circuit. 2 of them have a value of 0 ohms, and the other 2 have a value of 7.5 ohms each, in parallel. These resistors are essential for the proper functioning of the circuit, and their failure is interrupting the current flow. Replacing them is crucial to restore the proper functionality of the switching power supply. Next, I will analyze and measure each component in the MOSFET gate drive circuit. This circuit is crucial for controlling the switching of the MOSFET transistor, and any faulty component can lead to abnormal behavior of the entire system. I will check each component, including resistors, capacitors, and diodes, to ensure they are functioning properly and that there are no defects that could affect the performance of the circuit. From the measurements, it appears that only the transistor Q2, marked with the SMD code ZG, which is directly connected to the MOSFET gate, is faulty. This seems to be the component that is not functioning properly and is preventing the correct switching of the MOSFET transistor. Replacing this transistor should resolve the issue and allow the circuit to function normally again. I also measured the power MOSFET transistor, which seems to be fine. I did not observe any defects or abnormal resistance in this component, suggesting that the MOSFET transistor is functioning correctly and is not the cause of the issue in the circuit. I will now proceed with replacing the defective components, the 4 resistors, and the Q2 transistor. This process is quite meticulous, as all the components are SMD, surface mount device. SMD components are much smaller than through-hole components, so working with them requires great attention and precision. First, I need to use a soldering iron with a fine tip to avoid damaging the PCB or surrounding components. It's important to ensure that each component is correctly aligned, the polarity is followed properly, and the soldering is clean and solid. This process demands patience and precise technique to ensure the inverter will function correctly after the repair. To ensure that the soldering is done correctly and the connections are solid, I will use flux gel. Flux gel is an essential material in the soldering process as it helps clean the surfaces of the components and the printed circuit board, removing oxide and other impurities that can interfere with proper soldering. Additionally, flux gel improves adhesion between the component and the circuit board, ensuring a more efficient electrical connection. Flux gel allows for more controlled application compared to liquid flux since it doesn't flow easily, providing better precision when soldering SMD components. After applying the flux, I will use a fine-tipped soldering iron, maintaining a steady temperature to melt the correct amount of solder. Once the soldering is done, I will check each connection to ensure there are no short circuits and that each component is securely attached to the board. After finishing, I will clean any excess flux left over to prevent potential electrical issues in the long run. Instead of the two 7.5 ohm resistors, which were connected in parallel, I will use three 10 ohm resistors, also connected in parallel. The goal is to achieve a resistance value that is as close as possible to the 7.5 ohms needed. When resistors are connected in parallel, the total resistance decreases. In the case of the three 10 ohm resistors, the total equivalent resistance will be lower than the value of a single 10 ohm resistor. After calculation, the resulting resistance will be approximately 3.33 ohms, which is fairly close to 3.75 ohms, the equivalent of two 7.5 ohm resistors in parallel. Thus, by using three 10 ohm resistors, I can achieve a reasonable equivalent resistance value that is enough to temporarily replace the 7.5 ohm resistors, even though it is slightly lower. This is a temporary solution until I can find the correct 7.5 ohm resistors. After powering the inverter with 230V, I check the switching signal at the MOSFET gate using the oscilloscope. The oscilloscope display shows that the switching signal is present. Now, I will mount the electronic board with the display facing up to check the results. This will allow me to observe the output and ensure that the inverter is functioning correctly with the repairs made. The placement of the board is crucial for proper alignment with the other components and for accurate visual feedback from the display. Once everything is connected and secured, I will monitor the system to ensure it operates as expected. As seen on the display, a frequency of 30 Hz appears, which is preset in the inverter's operating parameters to serve a specific type of equipment. This frequency is the start frequency, or the initial operating frequency at which the inverter begins to supply the power signal. It is set by default to ensure compatibility with equipment that requires a specific frequency at startup, and it can be adjusted later based on the application or the connected equipment's requirements. Next, I will connect a potentiometer to adjust the output frequency of the inverter. Instead of a motor, I will use 3 230-volt light bulbs connected in a star configuration, with the purpose of verifying the presence of the output voltage. Incandescent bulbs are used because I don't have a small power motor at hand, but they are sufficient to demonstrate the inverter's operation. The bulbs will be used only as a visual load to confirm that the voltage signal is present. So, that was the repair and testing of the LS Electric M100 inverter. I hope it was helpful and that you learned something new about the process of diagnosing and replacing electronic components. If you liked this video, don't forget to give it a like, leave a comment with your thoughts or questions, and, of course, subscribe for more interesting electronics projects. Thank you for watching, and I'll see you in the next video.